Welcome to The Explainer. Today, we're decoding the invisible rules of our physical world. We're going to take the raw, unfiltered laws of physics and translate them into the practical, real-world engineering that literally shapes absolutely everything around us. It's this fascinating jump from abstract theory to the concrete reality we interact with every single day. So we're going on a little journey, starting from the macro concepts of massive physical structures all the way down to the micro language of math. Okay, let's dive into this. On our agenda today, the world of mechanics, simplifying our reality, Newton's fundamental laws, understanding force systems, and finally, the language of vectors. Let me start by throwing a high-stakes question your way just to ground all this. How exactly do engineers guarantee that a massive, thousands of tons skyscraper won't just tip over in the wind or completely collapse under its own immense weight? I mean, it kind of seems like magic, right? But it's actually entirely predictable. The answer lies in the unseen forces at play in everyday life. As you'll see, the exact same invisible rules of applied mechanics that governed that towering skyscraper, they're the exact same ones dictating how you sit perfectly balanced on a simple chair. It's all about forces pushing and pulling and how materials resist them.
Section 1, the world of mechanics.
So, what exactly is this field, and why do engineers rely on it so heavily? Well, applied mechanics is really just the practical application of physical laws to solve real engineering problems. This family tree brilliantly illustrates how vast the field actually is. It branches out quite a bit. We've got the mechanics of fluids over on the right and the mechanics of solids on the left, which then splits again into deformable bodies and rigid bodies. And all of these highly specialized branches exist for one unified purpose, making sure structures and machines stay safe, stable, and efficient whenever they're hit with various forces. Now, when we zoom in specifically on rigid bodies, engineering mechanics actually subdivides into two very distinct areas. Take a look at the contrast on the screen here. On the left, you've got a block being pressed firmly into a surface by a downward arrow. And on the right, there's a figure actively pushing a block forward with a horizontal arrow. Which brings us to a pretty fundamental definition. Statics is the study of bodies at rest or in a state of equilibrium, exactly like that image on the left. Dynamics, on the flip side, is the study of bodies in motion, like the one on the right. So whether a bridge is staying perfectly still under the crushing weight of rush hour traffic, or a robotic arm is whipping around to assemble a car, mechanics gives us the exact framework to understand and predict that behavior. Section 2, simplifying our reality. But let's be real for a second. The actual world is incredibly messy and complicated. Materials have hidden flaws, wind is unpredictable, shapes are all over the place. To actually make the math work, engineers need some really clever shortcuts. We use models or idealizations to simplify how we apply the theory. So the crucial point is how these three main idealizations let us do that. First up, a particle. This has mass, but its size is so unbelievably small we can just ignore it. Think of modeling the entire Earth as a simple particle when you're calculating its massive orbit around the sun. Second is the rigid body. This model assumes that all particles in a body stay at a fixed distance from one another. Basically, the shape absolutely does not change when a load is applied, which lets us temporarily ignore the specific material type. And third, a concentrated force, which assumes a spread-out load acts squarely at one single precise point. Section 3. Newton's fundamental laws. But what actually dictates how these idealized objects behave out in the wild? Well, we're talking about the unbreakable laws of nature that serve as the absolute baseline for all engineering. I'm going to pace you through these three chronological steps governing how physical objects interact. First is inertia. A body just continues in its state of rest or uniform motion in a straight line unless some unbalanced external force messes with it. Second, the undeniably famous F equals ma. An unbalanced force applied to a particle of mass m creates an acceleration a that is directly proportional to that force. And third, action and reaction. The mutual forces between two particles are always equal, opposite, and collinear, which just means they act along the exact same straight line. You push a wall, the wall pushes back with the exact same force, no exceptions. Building directly on those, we get Newton's law of universal gravitation. This defines gravitational attraction, stating that every particle in the universe literally attracts every other particle. It's wild to think about. This force grows with the product of their masses, but it shrinks exponentially, inversely proportional to the square of the distance between them. When we apply this law to a mass near the surface of the Earth, this mutual attraction is exactly what gives us the everyday concept we simply call weight.
To make this universal law actually work mathematically, we have to use the universal constant of gravitation, g. And honestly, look at this exact mind-bending number, 66.73 times 10 to the negative 12 meters cubed per kilogram second squared. It is an astoundingly small number, but it is literally the precise mathematical glue that binds our entire physical universe together.
Section 4. Understanding force systems. Now that we've got the foundational laws of gravity and motion down, we have to recognize that in reality, objects rarely deal with just one isolated force at a time. They are bombarded by multiple forces all at once. A force system is simply a collection of forces acting on a body. To make sense of all this chaos, we logically categorize them based on where their lines of action exist. As you can see in this table, forces are coplanar if they share the exact same plane, or non-coplanar if they operate in different 3D planes. On top of that, they're concurrent if their lines of action all mathematically intersect at one single point, and non-concurrent if those lines never ever cross. Notice the arrows here. This gives us a perfect, concrete visual of a coplanar concurrent force system. All these forces, labeled P1 through P4, are acting flatly on the same plane, kind of like you just drew them on a single sheet of paper, and their lines of action all intersect right there at that central origin point. But what about non-coplanar concurrent forces? Well, think of forces meeting at a common point, but operating out in 3D space. It's exactly like the 3 separate legs of a tripod firmly supporting a camera. That is just a highly relatable, brilliant everyday example of multiple angled forces resolving perfectly at one central equilibrium point. Section 5. The language of vectors. All right, to reliably predict and measure all of these complex pushes and pulls, we're going to need some specific mathematical tools. We have to make a very sharp distinction here between two physical quantities. A vector requires both a magnitude and a direction. Think of force, position, or physical moment. A scalar, on the other hand, requires only a magnitude. Things like length, mass, and time, those are scalars. 10 kilograms is just 10 kilograms, no matter which way you face. But when we're mapping structural forces, we absolutely must use vectors because the direction of the push matters just as much as how hard you're pushing. Now, what's really interesting about this slide is how it breaks down the parallelogram law. It's such an elegant solution to a complex problem. If two vector forces act at a single point, we can figure out their total combined effect, the resultant force, by representing them as adjacent sides of a parallelogram. Their true sum is simply the diagonal passing through that common point. It's basically this clever geometric trick for adding separate forces together so we can see where an object is actually going to go.
When engineers have to move past simple 2D geometry and start mapping complex 3D space, they use Cartesian vectors. We break forces down into x, y, and z components using the dimensionless unit vectors I, j, and k. You can think of these simply as directional road signs for the math. This lets us mathematically express a complex force as F equals Fx plus Fy. By utilizing these tools, along with operations like the dot product to find angles between lines, engineers can systematically resolve incredibly chaotic webs of pushes and pulls into clean, solvable algebraic equations.
And that brings our exploration full circle. From the macro behavior of a rigid body all the way down to the precise vector math that defines its equilibrium. So I'm going to challenge you. Look around your room right now. Can you identify the unseen forces of statics and dynamics keeping your environment perfectly balanced? Think about the coplanar concurrent forces holding up the desk you're sitting at. Because honestly, once you learn the language of applied mechanics, you realize these invisible rules are absolutely everywhere. Thanks for hanging out with me on this explainer, and keep questioning the physical world around you.